Hello chemists, this is Ms. Placino and you are watching Screencast 7.5 on gas laws. Today we're going to talk about how gases are going to behave under changing temperatures, pressures, and volumes. So gases are really sensitive to changes in these three variables, in particular pressure. Solids and liquids don't really respond to pressure changes, but gases, since they have such large spaces between molecules, are going to be very sensitive and very responsive to changes in pressure. So we're going to talk about a handful of different gas laws today, and things are going to get kind of mathy. So if you don't have it out already, you should grab a calculator and something to write with. All right, so let's jump right into it. Just to remind you, there are some conversions that you're going to need to know so that you can solve these problems. We'll start with pressure first. I'm not overly concerned with the definition of pressure. It's just the force per unit area on a surface. We're going to use a barometer to measure pressure. Basically, the way a barometer works is the atmosphere presses down on this pool of mercury, and the harder the atmosphere presses, the farther up the column the mercury will travel. So we can measure pressure in a variety of different units. Here are some that I'd like you to be familiar with. We've got 1 atmosphere is equal to 760 millimeters of mercury. That's literally what you'd measure. In a barometer, Torricelli is credited with inventing the first barometer, so he gets an honorary name unit. Sometimes you'll see it capitalized, sometimes you'll see it lowercase. I'm actually not sure what the official way to represent it is, but we call millimeter of mercury and a torr, they're the same thing. For those of you who have a bicycle, you might know PSI is pounds per square inch for your bike tires, and you've got 101.3 kPas. The 1 ATM and the 101.3 kPas is on your reference table on table A. The 14.7 psi is going to be helpful in the quest homework, but I'm not going to ask you to memorize that one. Really, the only number that you kind of have to commit to memory is a 760 torr. All right. If we've got a thermometer, we are measuring temperature. Again, I'm not super concerned about the definition. It's just the average kinetic energy of a sample. And we've got to be able to convert in between Kelvin and Celsius. So it's a really simple conversion. Take your Celsius temperature and add 273. For all the gas laws that we're going to talk about in this lesson and future lessons, you want to make sure that you're working in Kelvin. It is not okay to express temperature in Celsius. It's not all going to work out. Once we get into some examples, we'll talk about why it is so important that you use this formula and you convert out of Celsius and get it into Kelvin. All right, let's talk about some gas laws. So first we have Boyles Law. Boyles Law is looking at the relationship between volume and pressure. So if you look at this graph, hopefully you notice that this is an inverse relationship. As pressure increases, volume decreases. And that should make sense. If you think about holding a balloon and then you start pressing on it, you can push those gas particles closer together, decreasing the volume, and you've increased the pressure. So as pressure increases, volume is going to decrease. Again, an inverse relationship. We use this formula, P1V1 equals P2V2. So usually the way a Boyles Law question will work is we'll give you some initial or some starting pressure and volume. Then we're going to tell you, oh, now the volume is suddenly different, and you've got to figure out what the pressure is. It doesn't really matter what units you work in for pressure and volume, just be consistent. In other words, don't pick torr for pressure for P1 and then try to express pressure in atmospheres for P2. You're setting yourself up for disaster. So I don't care what unit you use, but you have to be consistent. All right, up next, we've got Charles's Law. Charles's Law is looking at the relationship between the temperature of a gas and its volume. From the plot, hopefully you can see that this is a direct relationship. As temperature increases, volume will increase as well. You can imagine taking a balloon and heating it up and getting those gas particles to move around more rapidly. And as that happens, the balloon should expand. I guess this is a little bit hard possibly to understand how it's written, but we have volume 1 over temperature 1 equals volume 2 over temperature 2. For the volume, I don't care what units you use. For the temperature, you have to be in Kelvin. Let's take a minute and talk about why that's the case. If you have something in degrees Celsius, it is possible to have a temperature that's equal to 0. Why is this potentially a bad thing for your gas laws? Well, if you look at the way the formula is set up, you are going to be dividing by temperature. So if you divide by 0 from math class, you know that this is undefined. So that's not going to work. Also, when we are working in Celsius, it is possible to have temperatures that are less than 0. So that would give us a negative temperature, meaning when you go through and you do the calculation, you get a negative volume. And if you think about it, that really doesn't make any sense at all. And for these two reasons, you want to make sure that you are not working in Celsius. You need to convert to Kelvin before you get doing anything else with the gas law itself. The third one is Gay-Lussac's law, and Gay-Lussac's law is looking at the relationship between temperature and pressure. Now, instead of a balloon where you've got those flexible walls, picture like a solid metal container. As you heat up the gas particles and they get moving faster, they're going to smash into the sides of the wall and into each other at a much greater speed or with more force, and therefore pressure is going to increase. So as pressure increases, temperature increases. We've got a direct relationship set up, so we've got P1 over T1 is equal to P2 over T2. As with Charles's law, I don't care what units you use in the numerator, surprise me, but in the denominator where there is temperature, you have to work in Kelvin, absolutely. Okay, so before you start panicking about how many formulas you are responsible for, a couple of things. First off, I'm never going to ask you the formulas by name. I don't care if you know if it's Boyles, Charles, or Gay-Lussac's. As long as you can apply the information, I'm perfectly happy, so you don't have to stress about memorizing names. If you're a little bit stressed about dealing with the formulas, well, New York State feels your pain. While you won't have all three of those formulas on your reference table, they will give you this one, and this is called the combined gas law formula. This is why this one is so helpful. Let's say you're looking at the relationship between pressure and volume, which is Boyle's law. Pressure and volume is, Boyle's law is P1V1 equals P2V2. Oh, if you cross out the temperature term, because that's not changing in that example, that's exactly what you get. If you're talking about Charles's law, which is going to be the relationship between volume and temperature, you just cross out the P's, and you've got the right relationship, the right format. Volume over temperature is equal to volume over temperature. So while we haven't provided you with the three individual formulas, you do have the combined gas law formula that can be really helpful. So all the other gas laws that we talked about can be derived from this equation. And again, New York State was kind enough to provide it on the reference table. Look at, I think it's table T on the back page. All right, let's do a little bit of practice. I know there are not a ton of questions here to work with, so we'll just do a couple. And really, for the most part, this is just straightforward plug and chug. Make sure that you have units that are in agreement with each other. In other words, that you are using torr or liters on both sides of the equation. Don't mix and match. And when it comes to temperature, you have to work in Kelvin. Let's look at question number 2. Zoom in on that. A balloon is filled with air. A balloon filled with air is at 25 degrees Celsius and has a pressure of 700 torr. The balloon is then submerged in liquid nitrogen, bringing the temperature down to negative 70 degrees Celsius. What is the new pressure inside the balloon? All right, so I need to figure out which gas law I'm using, and the best way to do that is to take a look at the information you've been given. Most specifically, look at the units. So I see a degree Celsius. I see torr, degrees Celsius again. So I definitely have temperature with Celsius, and torr is a unit of pressure. So I need the relationship between pressure and temperature. I'm just going to write my combined gas law up here, so I don't have to flip back and forth between this and the reference table. I'm concerned with pressure and temperature. That means I can just cross my volume term out, essentially. And that sets up my relationship. It's going to be P1 over T1 equals P2 over T2. Do I have to write that down? Yes, of course. Show your work. It only takes an extra second or two. They can save you from making some really careless mistakes. Okay, up next we need to plug in our information. So we know we initially start with a pressure of 700 torr. I'm trying to find what the pressure is at the end, so I'll leave that as a variable, and I can plug in my temperature terms. But before I do that, what has to happen? Yeah, I cannot leave it in Celsius. I've got a negative temperature here. Even if this was positive 70 degrees, it wouldn't matter. I still need to convert into Kelvin. So the temperature in Kelvin is equal to 273 plus the temperature in Celsius. I'm not super concerned with you showing me this formula. I trust that you can add or subtract numbers from 273. So we've got 25 degrees Celsius. That's going to be equal to 298 Kelvin. And negative 70 degrees Celsius, that's going to be equal to 203 Kelvin. And that's really it. Now you're just set up for a simple algebra equation. I've got 700 torr times 203 Kelvin, and then I'm going to divide that by 298 Kelvin, and that's going to leave me with an answer in torr. If we assume this is 700 point, we can take some more sig figs, and I come up with about 477 torr for P2. There we go. All right, now let's do another one just to make sure we've got the hang of this. Let's go ahead. Excuse me. Let's do number 3. Why not? You know what? No, I changed my mind. Let's do number 6. A meteorological balloon contains 235 liters of neon at 24 degrees Celsius and 0.854 atmospheres. It will burst if the volume reaches 394 liters. At what temperature will the balloon burst if its pressure at the bursting point is 0.535 atmospheres? Oh wow, lots of information in here. Just like I did with the last question, I'm going to focus in on the units. So I see liters, I see degrees Celsius, I see atmospheres, I've got liters again, I've got atmospheres again. So I've got liters, which is a volume, Celsius, a temperature, atmospheres, a pressure. So I've got all 3 variables that I have to keep track of. So this is pointing me at the combined gas law. And I'm going to start writing up here a little bit just so I have more space. P1V1 over T1 is equal to P2V2 over T2. It was pretty nice here, and I gave you things in the same unit. So for example, the volume of both V1 and V2 is in liters. Pressures and atmospheres, that's going to make life a little bit easier. So my first pressure is 0.854 atmospheres, and the first volume is, where'd it go, 235 liters. I'm going to divide that by, battery, go away. Maybe not. Sorry. I know I start with a temperature initially at 24 degrees Celsius, so 24 plus 273 gives me 297 Kelvin. And then I got to fill in on the other side. It's asking for the temperature, so I'm going to keep T2 in my denominator. And I've got my new pressure, which is 0.535 atmospheres. Times the volume, 394 liters. And now that's it. Be careful about how you punch this into your calculator. It's really easy to kind of make small mistakes and flip around numbers or just get careless with how you solve. But I want to take 297, multiply that by 0.535 atmospheres, then multiply that by 394 liters. Then I'm going to divide by 0.854 atmospheres, and then divide by 235 liters, and that's going to give me T2. In this case, I see 3 sig figs pretty much everywhere. So I end up with a final answer of about 3,120 Kelvin. Okay, so like I said, there are a couple other practice problems here for you to play around with, but basically they tend to be straight plug and chug. What I mean by that is you take your information directly from the question and you have to plug it into the right locations and the right spaces in the formula. That's one of the reasons I really encourage you to write the formula every time you use it. You're probably sick of me saying it by now, but to be quite honest, I'm sick of not seeing it on your papers, so get in the habit. It's going to save you from making careless mistakes. All right, that wraps up today's lesson. Thanks for tuning in, and I hope this was helpful.